So, it's time to talk about op-amps. Oh, don't give me that look. You knew this video was coming eventually. Of course I had to talk about op-amps sooner or later. What catalyzed this was that someone messaged me on Reddit and said, "Hey dude, you seem like you know a lot about op-amps." Well, no, I really don't. Op-amps are a Mount Everest-sized pile of knowledge, and I am I'm not even at base camp when it comes to op-amps, but compared to this person, I actually did know at least basics. So the best way to start understanding op-amps is to understand something called an ideal op-amp. Now, an ideal op-amp is not real. It doesn't actually exist. Instead, it is a simplified model that gives you a good mental framework for thinking about how op-amps work, and it can be extended so that you can understand how real op-amps work by understanding the non-idealities in real op-amps. In my opinion, a lot of places don't actually explain op-amps well. A lot of textbooks just throw an equation at you and assume you're going to figure out everything from there. So I wanted to take a short video and tell you a little bit more about op-amps. I will put this page in the description. This is my personal favorite page for explaining op-amps, and I think it does it in a way that a lot of other textbooks and other sources don't do it. So let's scroll down here and first look at just a picture of an op-amp. This is the circuit symbol for an op-amp. You can see it has two inputs and one output. Don't worry too much about the names. It's not really important just yet. The important thing to know is that you put two inputs in, usually these are voltage inputs, and you get something out, which usually is also a voltage. Now this basically is how the op-amp works inside. It is a two-step process. That's really important. Remember that when you think about op-amps, there are two steps going on inside the op-amp. The first thing that happens is it takes the plus input voltage and then it subtracts the minus input voltage. Let's say this input was 4 volts and this input was 3 volts. The op-amp does 4 minus 3 and gets plus 1. That's the first step. The difference between the two input voltages is calculated. It is the difference in voltage between them that matters, not the absolute voltage on the inputs. This block will give you the same answer with 1.1 volts and 1 volt, or 15.1 volts and 15 volts. The difference between the two voltages is 0.1 volt either way, and 0.1 volt will come out of here. Then the second step is it takes whatever the output of that was and multiplies it by a huge number. Usually this is never less than 1,000. Sometimes it's as high as 10 million. That's not really important. The important thing to know for an ideal op-amp is whatever difference in voltages, whatever the difference between these two input voltages is, gets multiplied by a huge, enormous amount, and then that is sent out the output. So in this case, we had 4 volts on this input and 3 volts here. The difference is 4 minus 3 equals 1. 1 volt times a huge number, let's say 1,000,000, is theoretically, for an ideal op-amp that doesn't have any real-world limitations, would be 1,000,000 volts on the output. And this op-amp, because it's an ideal op-amp, it's the god of all op-amps, it has no problem putting out 1,000,000 volts on its output. At this point, you may think, well, that sounds really simple, but there's a couple subtleties here, and these subtleties came up in my conversation with the person who I talked to on Reddit. The first subtlety is that order matters a lot. Which voltage is on which input matters a lot. So whenever you're looking at an op-amp, you should always be very, very careful about your inputs and seeing what is on which input, and then doing this first step correctly. A lot of times they will flip this symbol upside down and they will put minus on the top and plus on the bottom. In which case you would actually have to do, instead of doing 4 minus 3, you would have to do 3 minus 4, get minus 1 out of the first stage, and multiply minus 1 by 1,000,000, which would be minus 1,000,000 volts at the output. So pay a lot of attention to which signal is on the plus and which one is on the minus. Honestly, I don't even like labeling these with plus and minus. I would much prefer to label them as like input 1 and input 2. And then when they give you the equation that they give you, they would give you V input 1 minus V input 2. And that way it would be a lot harder to mess them up. But they don't do that. So The next thing you probably need to know about op-amps is not only do they multiply the difference between the input voltages, they are frequently used with something called feedback. And feedback is where either all of the output voltage or some of the output voltage gets sent backwards around the op-amp and has an effect on the inputs. So let's shift gears here and get into Fallstad Sim, and I can show you the simplest example of using feedback in an ideal op-amp. This right here, where the output is simply fed back directly into the minus input, is the simplest op-amp voltage feedback circuit that I can think of. And what this does is purely to take whatever voltage is being presented on the plus input. Remember, it's very important which voltage is on what input. It takes that input voltage and it simply mirrors it to the output. You can see that I've got this voltage right here on a slider over here. So I can change what my input voltage is, and the output of the op-amp will just stay at exactly whatever that voltage is, regardless of how I change the input voltage. Remember, this is an ideal op-amp. An ideal op-amp does not have the limitations that a real one does. A real op-amp could not swing its output voltage to any old voltage, and it couldn't swing it there instantly. There would be some time lag going through the actual transistors inside the op-amp. But this is an ideal op-amp. It is perfect. It has no delays. It has no parasitic capacitances inside, and it can have an infinite range of output voltage, and it can output an infinite current. It can do whatever the hell it wants because it is the god of all op-amps. So this is pretty simple. Basically, you put in 2.5 volts here, and then let's say at the very beginning of things there was only 2 volts here. That 2 volts is fed backwards into the minus input, and it notices that there's a difference between those 2 voltages. And through a sort of iterative process, the op-amp is going to keep changing the voltage on the minus input over and over again until that voltage matches what's on the plus input. So the op-amp is actually playing an active part in this circuit. It's seeing what the voltage on the plus input is, and then the minus input is seeing what voltage is on the output. Then whatever the difference is between those 2 voltages, the op-amp is going to try and swing its output voltage to eliminate any difference between those 2 voltages. And since the output is connected directly back to the minus input, the net effect of this signal going around and around here is that the output voltage will eventually become the same as the input voltage, minus some non-idealities that real op-amps have. Real op-amps can't necessarily sense the voltage at their inputs perfectly, so this might be, exactly 2.5 volts, but it might get sensed as 2.495 volts, and then that, of course, will change the outcome. Also, not all op-amps, especially the non-ideal op-amps, can supply infinite current. So if you have a very small resistor here, like a 1 ohm resistor, or if you had a capacitor over here, capacitor needs some current input to charge up. Those are non-idealities that I don't want you to worry about right now. Just understand that if you want a buffer to buffer a voltage, then this simplest op-amp application is probably a reasonable way to do it in a lot of cases. So that's the first op-amp thing I want you to know about, is an op-amp buffer that allows you to take an incoming voltage that could be from a very weak source, like it could be from a resistive divider made of 2 mega ohm resistors. But an ideal op-amp does not have any current coming into or out of the inputs. The inputs are perfect, and they will not change anything about the voltage coming out of a voltage divider if there were one over here on the input. Op-amp buffer uses feedback to drive the minus input to the same voltage as the plus input, thus eliminating any difference between the 2 of them. Now let's make this a little bit more interesting. All right, look what I've done here. I've taken this output voltage out of the op-amp, and I've run it through a voltage divider. And now, instead of sending the full output voltage back to the minus input, I have only sent back half of the input voltage. Let me actually show you. So the output is 4 volts. That's the output voltage of the op-amp. And that goes through a 2-to-1 voltage divider and becomes 2 volts. Actually, I think this would be more interesting if this was 3 volts here. Hang on a sec. Okay. We put in 3 volts. There's some amount of voltage on the output. Who knows what it is? Whatever it is, half of it gets delivered back to the minus input. Now, if there is any difference between half of the output voltage and what's on the plus input, the op-amp is going to change. And so as the signal runs around and around and around here, eventually the op-amp is going to do whatever it can to minimize the difference in voltage between its two inputs. Which means that eventually the minus input is going to become, in an ideal op-amp anyway, exactly the same voltage as the plus input because of this signal going around and around and around and chasing its own tail until it finally catches it. And the point it catches it is the point at which the plus input and the minus input have the same voltage. And because I've tinkered with how the output voltage gets back to the minus input, because I've put a resistive voltage divider in here to ensure that only half of the output voltage makes it back to the minus input, what I ended up doing here is making a voltage doubler. This 3 volts will be doubled to 6 volts on the output. Why? Because only half of the output gets fed back. Essentially, I've asked the op-amp, what kind of output do I need in order to create an equal voltage on the plus and minus inputs? And the answer is, if you have a 2-to-1 voltage divider, then you will need 6 volts at the input of the voltage divider to get 3 volts on the minus input. And that is how you match up the plus and minus input voltages by having a 6-volt input to this 2-to-1 voltage divider. For an ideal op-amp that can supply an infinite amount of voltage, either positive or negative, you can very easily change these resistors to change the amount of multiplication going on. Let's say I want to multiply this input voltage by a factor of 10. I would need to make a 10-to-1 voltage divider. So let's just do it. A 10-to-1 voltage divider would mean we would need a 9K resistor up top and a 1K at the bottom, or whatever. If you want to use 90K and 10K, it is the ratio of the resistors that matters. So let's just make this a 9K resistor. Boom, 10-to-1 voltage divider yields a 10 times multiplication of the input voltage. The input voltage is 3, the output voltage is 30 volts. So this is the second easiest op-amp with feedback application, which is it's both a buffer and it's a multiplier. And the reason it's a multiplier is because you're tricking the op-amp by only feeding back some portion of the output voltage back to the minus input. And because the op-amp will try to swing its output voltage in whatever way it needs to in order to make the plus and minus inputs have the same voltage, if you trick it by only feeding back some of the output voltage back to the minus input, then it's going to swing its output up and down to try and do whatever it can in order to make its two inputs have an equal voltage. And again, this is a consequence of the way that the op-amp works internally. It's a 2-step process. And when you run feedback around this loop, the signal will run around and around and around, and hopefully it will stabilize. That's a non-ideality, but hopefully it will stabilize, not turn into an oscillator where it's swinging its output back and forth as fast as possible. That's a problem. But in an ideal op-amp, where there's no time delay through the 2 stages, that signal will self-correct until there is no difference between the voltages on the 2 inputs, which allows you to do fancy tricks like this. Now, there is much, much more to explain about op-amps than this thumbnail sketch that I have given you here. The concept of feedback and having the op-amp steer its output voltage either up or down in such a way to try and create the right voltage at the minus input is an extremely powerful technique and can be used in all sorts of unexpected ways. For instance, the output of this op-amp could control the base of a bipolar transistor. Then you could measure a voltage on the other side of that bipolar transistor, feed that voltage back to the minus input, and then the op-amp would try to do whatever it needed to do with its output voltage in order to make the voltage on the other side of the transistor be equal to what is on the plus input. And you can make precision current sources and sinks that way. There's all sorts of things you can do. Finally, this feedback network can be even trickier than what you see here. You can add capacitors and inductors into this feedback network so that the feedback network prefers to feed back some frequencies and not other frequencies. And when you do that, what you've made is something called an active filter circuit, where the op-amp is actively amplifying some frequencies and actively attenuating others. So op-amps are a very powerful thing. I think they're very misunderstood, and I think they're often taught badly. But if you want to get an idea of how to think about op-amps, this is the model you need to think of in your head. Now, if you'd like to see some more things that op-amps can do, let me show you the Wikipedia page on op-amp applications. I will also drop this page in the description. You can do an inverting amplifier, where you multiply the input voltage by a negative number. We've already talked about the non-inverting amplifier. There's the voltage buffer we talked about. You can take the sum of multiple input voltages and have that as your output voltage. You can have extremely low input requirement amplifiers. For instance, if you've got a strain gauge or other Wheatstone bridge that has extremely small currents coming out, you can make an amplifier that will amplify that and draw almost no current on the input. You can even build oscillators out of op-amps. You can see they've got RC filters in the feedback loop of this guy. And not only that, they're feeding back this signal to the minus input, but they've also put a feedback network on the plus input. Complicated advanced stuff, but very cool. Finally, you can also do integration and differentiation with an op-amp. All right, that's all I wanted to talk about with op-amps. That's the thumbnail sketch. There is an enormous amount of knowledge. Like I said at the beginning of the video, op-amps are a Mount Everest-sized pile of knowledge, and I certainly do not claim to know everything there is to know about op-amps, especially when it comes to things like phase margin calculation, Bode plots to find out which frequencies are being multiplied and by how much. There's an enormous amount of knowledge out there, but I just wanted to give you a mental framework for how to think about op-amps, how they work, and how to understand feedback. Remember, both input voltages are sensed. There is a difference between those two voltages. The order in which they are subtracted depends on which one is connected to the plus input and which is connected to the minus input. And then whatever that difference in voltage is between the two, it's the difference in voltage multiplied by a huge amount, and that is your output voltage. And of course, there are a huge number of non-ideal characteristics in any real op-amp because no real op-amp is ideal. Ideal op-amps can have infinite output voltage. They can swing that voltage infinitely rapidly up or down. They have no limit on the amount of current that they can source or sink through the output. Those things are all wonderful, but in the real world, they're almost never true. The good news is you can usually design the circuit in such a way that it doesn't really matter. I hope you're having a good one, and please stay salty, my friends.